Hello dear students, welcome to Axiomaticos. This video is the part of the solution series for PhD entrance exam of mathematics conducted by Indian Statistical Institute. So we are here with this 2019 paper and this is the question number 4 for this paper. So let us have a look. Let f such that R to R be a C infinity function such that it satisfies fx is equal to 0 if and only if x belongs to z. So the question is saying that you are given with a function f which is infinitely many times differentiable, and it has a condition that it will be 0 if and only if x is integer. Now they are defining another function x from R to R with the condition that x dash of t is f of xt for all t belongs to R. Now your A option suggests us, not option actually, it's a part. So this part actually tells us that if z intersection with xt, so this is actually the range set for this function x. So it says that if z intersection with the range set of x is non-empty, then show that x is constant. We will not read part B, we will do it later. So firstly what we will be doing, we will be proving your part A. Alright, so see what's given to us. We are given with a C1 function from R to R, and it has a property that fx will be, I should write this belongs to C infinity. Now fx is 0 if and only if x belongs to z. Alright, now they are defining another function x from R to R with the property that x dash of t should be f of xt. Alright, now see, in your question, if f is infinitely many times differentiable, so will be x dash t. Since x dash t is composition of f over some composition xt. Alright, so see this thing that x dash t is f of something. That means because of this differentiability for f, we will get x dash t differentiable. Are you getting my point or not? So according to this, we can show that x dash t will be infinitely many times differentiable. Are you getting my point or not? So firstly, see this thing that they are using this term x dash t, that simply means that it's 1 times differentiable. Now if you will evaluate later on the later derivative, you will end up with this thing that it's infinitely many times differentiable. Alright, we will talk about this later also. Now if you are given with the functions which are infinitely many times differentiable, that indicates that somehow you have to use the Taylor series. Are you getting my point? So you need to show that this function is constant. Alright, so this is your part A, and they said that if z intersection xt is non-empty, is not equal to phi. What is the meaning of this thing? It has a simple meaning that there exists C belonging to their intersection. That means there exists C belonging to Z such that xt is equal to C for some t. So this is the actual meaning of the intersection non-empty. Now what you have to do, you have to show x is constant. Alright, see x dash t, you are given with that x dash t is f of xt. Alright, f of xt. Now if you will differentiate it again, what will happen? You will get f dash of xt dot x dash t. Alright, the chain rule. Now you know that f dash will exist because f is infinitely many times differentiable, and x dash t, they already defined it to be f of xt. Are you getting my point? That means it's twice differentiable. So this is what I was telling you earlier, that it's actually infinitely many times differentiable. You can see it from here. Alright, you got this. Now if you will differentiate again, then what you have to do, you have to use the product rule. So let us differentiate your this thing first. So you will get f double dash of xt dot x dash t. This will be the differentiation of this part. Now you have to keep second function as it is, plus now you have to differentiate this. So you will get f dash of xt whole square dot x dash of t. So see, x dash t we can take common from it. So x triple dash of t will be x dash t common I am taking. So what is x dash t? It's f of xt. So I am taking this as common. Now what you are getting? You are getting something here. Okay, I will not write that. You will get something here. Alright, after taking common. Now try to focus on this step, that f of xt is always a factor of the derivatives of this. Are you getting my point? What I am saying, I will write. F of x of t is a factor of xn of t. You got my point or not? So it doesn't matter how many times you differentiate this function xt, you will get f of xt as it's one of the factor. Now what is the importance of doing so? It is important in order to write your Taylor series. So now let us write Taylor series of, okay, I should mention this first, that continuing this process, we will get all the derivative. We will get all the derivatives. All right, all the derivatives. So see, now I can write your Taylor series in terms of C. I am writing in terms of C. I will tell you later why it's important in order to write in terms of C. So x of t, the Taylor series of x of t around C will be given by x of C plus x minus t minus c x dash of c plus t minus c whole square by 2 factorial x double dash of c, and so on. Let us write nth derivative also. So t minus c to the power n over n factorial x n of c. All right, so you will go with this thing. Now what was important is this thing, that f of xt is a factor of xn of t. This was important. So calculate xn of c. What is xn of c? Not c actually. Yeah, c. So see from here, from this thing, all right, from this thing, see it. This n is greater than or equal to 1. All right, so it is equal to f of x of t for some t. Let us write this t as t naught. All right, now it will be clear. Are you getting my point or not? So this xn of c is equal to f of x of t naught multiplied with something. We don't have to write this part. Are you getting my point? See from here, let us say you have to write x dash of c. You have to write x dash of c. Then what you will do? F x of t naught, because this is what we are getting from here. All right, I am just changing it to t naught. Mention this t naught. So you got this. Now x of t naught is actually a what? X of t naught is actually a integer, because it is equal to c, and c is a integer. So that's why it's equal to f of c. Now you know that for an integer your function will give you 0. So whatever terms are here, we don't care about them, because we know that for every derivative f of xt is a factor of this derivative. So this thing is 0. So 0 multiplied with this, you got 0 as your answer. That means xn of c is 0 for all n greater than or equal to 1. Got my point or not? So every derivative which I have written here is actually 0. So everything will be cancelled. Are you getting my point? So finally we proved that x of t is nothing else, it's x of c. Now x is a single variable function and you are placing a constant inside of it. That's why we can say that your function is a constant function. So this is how we can prove that why your function will be a constant function. Got it? So now let us erase this space to solve this part B. Now in your part B, it's given to us that z intersection with the range set of this function x is empty. Then we have to show what? We have to show limit t goes to infinity, x of t exists and is a integer. So this is what we have to show. Now firstly try to understand the importance of this thing, that in the range set of xt you are not getting a integer. Firstly try to understand this thing with a graph, then we can directly write it down. So let us say this is your graph. Now you want to draw the graph for the given function xt. So let us denote this as t-axis and this as xt. You want to draw the graph. Now can you draw a graph like this, random graph? On the positive I am drawing right now. You can draw it on the negative side, but let us talk about the positive only. Can you draw it like this? No, you cannot draw. Why? Because then let us say this is the integer point, these are the integer point on the axis, let us say. All right. So are you getting integer point here or not? Somewhere here. I'm not saying that it's exactly here, but you will always get, because it is intersecting. These lines are intersecting this. Let us say this is xt is equal to what? 3, xt is equal to 2, xt is equal to 1. So you will get an intersection with them, these lines. Therefore these points you will get your value of xt as integer. Are you getting my point or not? What I'm trying to make this thing clear in mind, that you cannot draw a random graph like this, because otherwise you will got an integer point in your range set. That means you have to always lie in between those two lines. If you want to draw the curve, you cannot go beyond these two lines or any random line. Let us say these two. All right. If you want to draw your curve, you cannot go outside of this line and outside of this line. You have to remain inside of that. In order to fulfill this property, you cannot go outside of these two lines. That means there exists, okay, because of this property, you can say there exists k integer such that your whole function lies inside of it. Xt lies between k plus 1 and k only, all right, for all t in belonging to R, let us say. Are you getting my point or not? So your function will completely lie in between these. All right. So now let us move forward. You got my point? So now let us erase this graph. Now see, you are always in between two integers, and also you are not touching these integers also. You are in between them. That means from here you can say that xt will never be 0. Even these integers are, let us say, 0 and 1, even though you will not get that xt is 0. Are you getting? for all t belongs to R. So xt is non-zero, sorry, xt is non-zero. From this thing you can say that xt is non-zero, because you will not get integers because you are in between integers, so you cannot get integer. So xt is non-zero. Now since xt is non-zero, from here you can say that xt is either xt is completely let us say that you have this xt, so from here you can say that x dash t, which is equal to f of xt. All right, so I think there is no meaning of this line. I should erase this. Just wait a second. All right, so xt does not belongs to z. What is the meaning of this? If xt is not inside your z, it means that f will never be 0. So I should focus on x dash t to be non-zero. Alright, so I focused on xt, but xt has no importance. That xt is non-zero, that has no importance, but importance is of x dash t. Now you are saying that x dash t will be non-zero because you know that f is 0 only when it takes input an integer quantity, but because you are inside in between two integer, you will never get integer quantity. That's why it's non-zero. All right, now what do you know? You know that if you have a function which is non-zero, okay, all right, this is infinitely many times differentiable function, and you have a function which is non-zero. So let me draw the Cartesian plane again, and it's non-zero. That means you cannot have a possibility that this function is sometimes increasing and sometimes decreasing. That function property will be vanished. Why? Because let us say you have a value, let us say t1, where your function is decreasing. Function is decreasing means x dash t is negative. All right, x dash t is negative. So this is, let us say, your x dash of t1, and let us say for some t2 point you have a positive x dash of t2. This actually means that at t1 your function is decreasing because it's negative, and at t2 it's increasing because it's positive. So we are trying to find out the possibility, can it happen? All right, so now according to the intermediate value property, if a function is continuous and it attains two values, then it has to attain all the values in between them. That means if it is attaining this value and this value, then it has to attain all those values between them. So that means it has to attain 0 also. So which is a problem, because right now you said that it cannot attain 0. So it cannot happen simultaneously that for some point x dash of t is less than 0 and for some point it's greater than 0. All right, it cannot happen simultaneously. So from here you can say that x dash t of is either greater than 0 for all t, or x dash t is less than 0 for all t. Are you getting my point? These two conditions cannot happen simultaneously, so they will happen. It may happen that this is happening completely or this is happening completely. All right, you got my point, I think now. So now let me erase this graph. So now move to this part. What you have to show that limit t goes to infinity, xt exists and is an integer. All right, so let us try to think over this issue also. Now you have a completely increasing function. All right, so use these thing now, that xt is in k and k plus 1, it's bounded, and let us say without loss of generality it's increasing, because you have two cases only. You can take a decreasing thing also. Without loss of generality, let us say x dash of t is, sorry, not x dash of t, it's xt. Let me erase that. All right, so x of t is increasing. Alright, I'm taking which possibility? I'm taking this possibility. That let us say this is happening. Now you have a bounded function which is inside k and k plus 1, and it's not only increasing, it is strictly increasing. Okay, I should mention that. It's a strictly increasing function. That means it will have asymptotes. Alright, so this means xt will have two asymptotes because it's a bounded function, and it is strictly increasing on r. That means it's going to have two asymptotes. We don't know what they will be, but it's going to have two asymptotes because you cannot draw a function, a continuous function, and let us keep this thing here. You cannot draw the continuous function in such a way that you keep them strictly increasing. All right, so just wait. All right, now let us understand this thing with this figure, that you have this Cartesian plane in your hand, and you have what? You have these two. Let us say, without loss of generality, this is k, and let us say this is k plus 1. All right, this is xt is equal, this is k and this is k plus 1. Y is equal to k plus this is k plus 1 and this is k. This is line y is equal to k and this is line y is equal to k plus 1. Now you have a function in between them which is completely strictly increasing, so it should look like this. Are you getting my point? So it can happen that these lines k plus 1 and k are asymptote for this. Also it can happen that there is a line in between these two lines which are asymptote. Then your figure will look like this. Are you getting my point? So I am trying to explain this thing, that it can happen that k and k plus 1 will be asymptote, but also it can happen that there is a line in between these two which will be asymptote. This can happen also. Now I am going to remove this. I am going to say I am going to prove that this condition is not possible, that these two random lines in between k and k plus 1 are asymptote. Let us name them. Let us say this is y is equal to a and this is y is equal to b. I want to tell you that this cannot be asymptote for this curve. All right. Now see, because this y is equal to a and y is equal to b are asymptote to this curve, this is your curve xt. All right. Now what is the meaning of asymptote? When you go towards infinity, your curve will act as this line y is equal to b. And when you will go towards minus infinity, it will act like a. You got my point? Now this means that when you go to infinity, your slope should go to 0, because you see this curve is going to be flat after some time. That means your slope will be 0 in the end. Now if your slope is 0, then actually what you are trying to suggest, that this x dash t is 0, limit x dash t is 0. What is x dash t? X dash t is f of xt. So that means this thing will be 0. You got my point? Now as t goes to infinity, if f of xt is going towards 0, that means this xt is going toward, integer quantity, because otherwise you will not get it, because it's a if and only if condition that fx will be 0. So xt is going toward integer. So what is x? Where is xt going? Xt is going toward b, which is in between these two integers. So if b is not an integer, that's why we can say from here that it will not go to random b and random a. your curve will have two asymptote only, and that will be k and k plus 1. Are you getting my point? From this thing we proved that asymptotes will be only k and k plus 1. So what is the meaning of k and k plus 1 to be asymptote? It means that limit t goes to infinity, xt exists and it's an integer. So this is how we can show your part B also. So it's little difficult question in order to prove in exam, but if you will think those things graphically, you will end up with all of these conclusion what I made here. All right, so thank you.